Okay, good morning, everyone. So we're going to start our lecture today. Right. Now, I just want to mention that, I keep on not finishing these lectures, and I apologize for that. But the main reason is that our classes are shorter than usual, right? So because of this lockdown situation, our classes are about I think like 15 minutes shorter than usual. Okay. So I end up not being able to finish things. Yeah, and I don't want to cut out the material because I think this is important knowledge. And so basically, I'm just going to finish as much as I can, and whatever I don't finish, I'm just going to push off to the next lecture. Okay, so yeah, sorry about that. Okay, now first of all, so now we're going to continue with the previous lecture, and then we've got a new topic also for today. Okay, so for the previous lecture, we were talking about so we saw how to use Bloom filters, right? So that's kind of so that was one randomized data structure. And then the next problem we were talking about was how to use randomization to determine whether two strings are equal to each other. Okay. Now, the setup for this problem is that you have these two parties, Alice and Bob, right? And so they each have an n-bit string. Okay, so if you just want to compare whether their strings are equal to each other, you can just send the string from Alice to Bob. However, we're imagining that these people are connected via some sort of communication network, and it's expensive to communicate on that network. And so therefore, you want to send the minimum number of bits possible, but still check whether these two people have the same strings. Okay. And so what we did was we took these strings and we looked at them as n-bit integers. Okay, and then after that, we compute this fingerprint of each string, which is the integer modulo some prime number. And then you simply transfer whatever this fingerprint is. And when you do that, this is going to take you log p number of bits instead of n bits. Okay, and then what we said is that this algorithm does not have any false negatives. Okay, meaning that if you have two strings which are if you have two strings which are equal to each other, then this algorithm definitely will say they're equal to each other. However, it is possible to have false positives, meaning that you have two strings which are not equal to each other, but this algorithm says that they are equal to each other. Okay, and this can happen when you have two strings which are not equal, but the prime that you choose divides the difference between these two strings. In that case, you have that the first string modulo p is going to be equal to the second string modulo p. So the fingerprints look the same, even though the strings themselves are not the same. Okay, and so we can't completely avoid this false positive situation. But what we can do is to try to minimize the probability that it occurs. And the way that we do this is that we're going to pick a random prime to take modulo with. Okay, and the goal is that if you take a random prime over here, then it's unlikely that this random prime will divide your difference. Okay, and if it doesn't divide the difference, then you do not have a false positive. Okay, so then let's look at the probability that if you pick a random prime, it does not divide the difference between the two strings. Okay, and so what we need is we need a few facts from number theory. Okay, so the first fact is pretty simple. What it says is that if you have a number t, okay, any positive integer, then at most you have log t number of distinct prime divisors. Okay, for this number. So for example, if you take the number 6, right, it's got two different prime divisors, 2 and 3. Okay, and basically this lemma says that you do not, any number does not have too many prime divisors. It only has a logarithmic number of prime divisors. Okay, and to prove this, it's actually quite easy because each prime divisor of t has to be at least 2, right? And then when you multiply all these prime divisors together, you're going to get a number which can be at most t. Right? Sometimes you might have repeated divisors, and so if you multiply all the distinct divisors together, you get something less than t. Okay. All right, and so okay, so then the product is less than t, and so therefore, if you actually have more than log t divisors, right, then when you multiply all of them together, since each of them is at least 2, right, and you have more than this number of them, then your product would be larger than t. Okay, and that's a contradiction. So therefore, this number does not have too many prime divisors. Okay, it's got at most a logarithmic number of prime divisors. Okay, so the reason this is useful is because remember that we're looking at these two numbers a and b as n-bit bit strings. Okay, so therefore a and b are both at most 2 to the n. Okay, the value of a and b are at most 2 to the n. And so therefore a minus b is at most 2 to the n. And so therefore by this lemma, you have that this number a minus b has at most n distinct prime divisors, right? Because you just take the log of this thing, right? So you have at most n distinct prime divisors. Okay, so this is the fact that we want to have for the algorithm. Okay, so that's the first part. The next part is this thing called the prime number theorem. Okay, so this is actually a very important and very non-trivial result from number theory. Okay, so we're definitely not going to prove this result or anything. But all we need is to understand what the statement says. Okay, and so what the theorem says is that it basically tells you how many prime numbers are less than another given number. Okay, so if you give me a number t over here, then the number of prime numbers which are less than t is approximately t divided by the natural log of t. Okay, yeah. So for example, if t is 1,000, okay, then it turns out that the natural log of t is something like 7. Okay, so that means that the number of prime numbers which are less than 1,000, okay, there are about 1,000 divided by 7 such prime numbers. Okay, so there are about 140 prime numbers less than 1,000. Okay, so there's some sort of approximate factor here, and we're not going to get into how good this approximation is. Okay, but as a first order approximation, this is a correct result. Okay, so so the reason we care about the prime number theorem is that it allows us to efficiently generate random prime numbers. Okay, and how do you do that? All you do is if you want to generate a prime number less than t, you just pick any number at random. Okay. And because there are lots and lots of primes less than t, right? There are about t divided by log t number of primes less than t. Then if you pick a completely random number less than t, you've got a pretty good probability that it's actually prime. Yeah, you got a 1 divided by log t probability it's prime. Okay, so for example, if you pick a number less than 1,000, okay, you've got a 1 in 7 probability it's actually prime. Okay, and then after you pick this number, you have to check whether it actually is prime or not. Okay, so there are different ways to do that, and one way is this thing called the Rabin-Miller primality test. Okay, so this is some sort of algorithm, and if you give this algorithm a prime number, this algorithm will always say the number is prime. Okay, however, if you give the algorithm a composite number, okay, there's a small probability this algorithm makes a mistake, and it says that the number is actually prime, even though it's not prime. Okay, so it does have some sort of error probability. Okay. However, what you can do is you can just run this Rabin-Miller test multiple times on a number to decrease the probability of a false positive. Okay, so if I give this algorithm some sort of input, right, and if the first time the algorithm says it's prime, I'm not really sure whether it's prime or not. Right? Maybe the number is actually composite and the algorithm made a mistake. So then what I'll do is I can just run this algorithm k times. Okay, and that's gonna so if the algorithm has, let's say, a 1/4 probability of making a mistake each time, then if you run it k times independently, then you've got a 1 divided by 4 to the k probability. Okay, so you can exponentially decrease the false positive probability. Okay, so basically, so in summary, we can actually efficiently pick random primes. Okay, because all you do is you just pick a random number and then you run it through this Rabin-Miller test several times, and if it keeps saying it's prime, then with high probability you have a prime number. Okay, so then now that we can generate random prime numbers, right? So let's see how large we want to make our prime numbers, right? Because we're doing this fingerprint of a modulo p, so let's see how large we want to make p. Okay, so what we can do is we can set t to be let's say n squared log n. then if you plug this value into the prime number theorem, you're going to get that the number of primes less than or equal to t is basically this thing over here. Okay, it's t divided by log t, and then if you simplify some stuff, you get this, and you end up with that there are about n squared primes less than t. Okay, order n squared primes less than t. Okay, and so yeah, and so now we're just going to pick a random number, a random prime number less than t. Okay, and to do that, you just keep picking random numbers until you get something which is prime by the Rabin-Miller test. Okay, so we assume that you can generate a random prime less than t, where t is this thing over here. Okay, and now let's analyze our false positive probability. Okay, so you only get a false positive if this random prime that you pick happens to divide a minus b. Okay, but what we know is that a minus b has at most m prime divisors by the earlier lemma that we had. Okay, and so if p divides a minus b, it must be one of these m prime divisors. Okay. However, we know that there are about order n squared primes less than t, right? We said over here that there are lots of primes less than t. Okay, and in order for p to actually divide a minus b, it has to be one of these n special prime divisors of a minus b, right? And so the probability that this happens is that, what's the probability you get one of these n prime divisors of a minus b? Okay, it's at most n divided by the total number of primes which are less than t, which is n squared. And so therefore, the probability that p divides a minus b is at most 1 divided by n. Okay, so you've got a at most 1 divided by n probability of getting a false positive. Okay, right. Are there any questions about this analysis? Okay, all right. So then what we need to do is, so we see that this algorithm does not have any false negatives. It's got a 1 over n false positive probability. And lastly, we need to look at how much data you need to transfer. So we're going to transfer log p bits, right? And log p is at most equal to log of t, right? Because p is less than t. Okay, and t is basically n squared times log n. So if you take the log of t, you get that this is order of log n. Okay, so this means that you transfer only order log n bits for this algorithm, as opposed to n bits. Okay. Yeah. Right. Yeah. So in summary, this is what you get. Okay. And if you want to make the algorithm perfectly accurate, okay, so you don't want any false positive probability, okay, then you can prove that you actually need to transfer the entire database, right? You actually need to transfer all the bits, which is order n bits. Okay. So here, by accepting a reasonably small error probability, right, you can dramatically decrease the number of bits that you send. Okay. So this is why it's a useful algorithm. Okay, so that is about string equality. Okay, so next we're going to look at another string problem, and this is about string matching. Okay, so for string matching, the situation is that again you have two strings, x and y. Okay, but now you're not checking whether x equals y. So let's say that x is longer than y. Okay, x is a longer string. So you're not checking whether x equals y. You're checking whether y is contained in x. Okay, so for example here, right, y, if this is a string y, then y is contained as a substring in x. Okay, yeah, so notice that we want y to be a substring of x, okay, not a subsequence of x. Okay, so in other words, y has to occur consecutively in x. Okay, there can't be any gaps where y occurs in x. Okay, remember we talked about this longest common subsequence problem, where there also you're looking to sort of match a string y to another string x. Okay, but in that case, you allow gaps in the match. Okay, in this case, for this problem we're looking at, we do not allow any gaps. Okay, so there has to be an exact copy of y somewhere in x, and you want to determine whether this is true or not. Okay. Yeah. Okay. So then, there are actually many algorithms to do this. Okay. There are many deterministic algorithms for doing this. For example, the KMP algorithm. But the problem with these algorithms is that they're kind of complicated. Okay. Yeah. So today, what we're going to see is a very simple randomized algorithm for solving this problem. Okay. And so this is called the Rabin-Karp algorithm, and it actually runs in optimal time, optimal expected time. Okay. Yeah. So this is going to be a this is a Las Vegas algorithm. Okay. Meaning that the algorithm always returns the correct answer, right? So if y is a substring of x, it will always tell you that exactly. Okay. So it always returns the correct answer, but the running time is a random variable. Okay. So in expectation, it runs in linear time, in m plus m time. Okay. But it's possible that it runs in longer time than this. Okay, and by the way, m plus m is actually the optimal running time. Okay, because m plus m is simply the sum of the lengths of the two strings. Okay, and in order to solve the string matching problem, you have to look at the entire string x and y. Right? If you don't look at the entire string, then maybe there's a match somewhere and you don't even see that match. Okay, so you need to look at the entire string, and that's going to take you m plus m time. Okay, and so this algorithm also takes m plus m time in expectation, and so it's actually it's optimal. Okay. All right. So to talk about this algorithm, I'm going to define some notation first. Okay. Sorry. What? I just need to look at one thing. Sorry about that. Okay. So the first thing is that again we're gonna so these two strings we're looking at. We're going to assume they're bit strings again. Okay, so they don't have like letters in them or anything. They just have 0, 1 bits. So therefore, again, we're going to look at these bit strings as numbers. Okay, and so suppose x is this thing over here. Okay, so we're looking at whether y occurs in x. So x is like large and y is small. Okay, all right. So x, let's say it's going to be n bits like this. And now we're going to look at, we're going to define a substring of x of length m, okay? And this substring is going to start at the jth bit of x, okay? So we're going to start at the jth bit, and then in total, we're going to take the next m bits, okay? Yeah, so for example, here, this is x4, okay? And the idea is that, this x4 represents a potential match between x and y at location 4. Right, because this x4 has the same length as y, and then so it can potentially match y, right? And it starts at position 4. Okay, so yeah, so basically what we should be doing is we want to compare, like, does do x and y match at position 1? So you want to look at x1 compared to y. Okay, if that doesn't match, you can look at x2 compared to y, x3 compared to y, and so on. All right, yeah, and so therefore y is going to match x if there exists some y, some j, okay, between 1 to this value over here, such that x of j is equal to y. Okay, if y occurs within x, it's got to match x somewhere at one of these j values. Okay, and it has to exactly match x at that location, right? And so therefore, now our problem becomes testing whether x and y are exactly equal at this location, at the jth position for some j. Okay, and we just saw this algorithm, right? The previous algorithm is a way to check whether two strings are equal to each other using fingerprints. Okay, so we're going to make use of the previous algorithm within the string matching algorithm. Okay, now to do that, we're first of all going to give an m plus m time Monte Carlo algorithm for string matching. Okay, and what this means is that here, the running time is fixed. It's always going to be m plus m. Okay, however, the algorithm is Monte Carlo, meaning that there's a small probability it makes a mistake. Okay, in particular, it might say that y matches x even though it doesn't. Okay, so if y does not match x, then if y does match x, then this algorithm will always detect that. Okay, but if y does not match x, then sometimes this algorithm makes a mistake and it still says that y matches x. Okay, Now later, we're going to convert this algorithm, we're going to convert this Monte Carlo algorithm to a Las Vegas algorithm. Okay. And when you do that, now this algorithm will never make any mistakes. Okay. If it says y matches x, then that's true. Okay. However, now the running time is going to become a random variable. Okay. So sometimes it might run for more than n plus m time. Okay. All right. So we're first of all going to talk about the Monte Carlo algorithm. Okay. And it's kind of similar to how the fingerprint algorithm worked, the previous fingerprint algorithm worked. Okay. So again, we're going to choose a random prime number, right? And we saw how you can choose random prime numbers of any size that you want efficiently. Okay. And so I'll tell you later how large we should make this prime number. Okay. But right now, let's just choose a random prime number. And now for every possible position where y matches x, okay, so for all of these j's, right, then you're going to look at x of j and also y as m-bit numbers, right, m-bit binary numbers. Okay, and then next you're going to compute the fingerprint of x of j and y, and you're going to see whether these fingerprints match. Okay, so the fingerprint is, again, we're just going to take x of j modulo p, okay, and then y modulo p. So those are the fingerprints, and you just compare those fingerprints. Okay, so if the fingerprints are different, okay, then definitely xj and y do not match, right? Because if x of j and y do match, then their fingerprints would be the same. Okay, so if the fingerprints are different, then we don't have a match at position j, so then we're going to go on to the next j. Okay. On the other hand, if if the fingerprints do match, right, then we're just going to say that y matches x at position j. Okay. And here's where you can get a false positive, right? Because sometimes you have that xj and y actually do not match. Okay, but because we're taking fingerprints, it looks like they match. Okay, so you could get a false positive situation over here. But we're going to see later how to bound that probability. That's not a large probability. Okay, all right. So then you're going to do this loop for all possible positions. Okay, so if after all these positions you never find a match, right? You never do this, right? Then you're going to say that y does not match x. Okay, so that's the entire algorithm. Okay, so basically we try every possible position and we just compare the fingerprints at those positions. Okay, so first of all, let's look at whether this algorithm runs correctly. Okay, so yeah, so suppose you consider x of j and y for some j. Okay, so so as we said, if the fingerprints do not match, okay, if you have this inequality here, then definitely x of j does not equal y. Okay, so therefore you don't have any false negatives. Okay. However, if you have that the fingerprints match, right, then as we said, either the string actually matches, either y actually matches x at position j, or it does not match. But in that situation, you must have that p divides xj minus y. Okay, just like in the previous situation, in the previous algorithm, if you get a false positive, the only reason is because p has to divide a minus b. Okay, so in this case, p has to divide this value here. Okay, so now we're going to bound this probability. Okay, and so we know that xj minus y, right? So both of these are m-bit numbers, so their difference is also an m-bit number. So by this previous lemma that we had, we know that this number has at most m distinct prime divisors. Okay. And so now we're going to choose our t value. Okay, our t is going to control how big we make this prime p. Okay, so you're gonna pick a prime for, between 1 to t. Okay, so how large are we going to make t? We're going to make t be this large. Okay, we're going to make it be n squared times m. Okay, times the log of n squared times m. And then p is going to be a random prime between 1 to t. Okay, so now if you apply the prime number theorem, you're going to see that using this t, you have about n squared times m prime numbers less than t. Okay, and so the only way that you can get a false positive is if P is one of the one of these m up to m prime factors of xj minus y, right? Okay, and what is the probability that this happens? Right, well, P in order to get a false positive, you have to be one of these m special primes, right? But in total, there are n squared times m primes less than t. So the probability that a random prime less than t is actually one of these special primes is going to be this thing. Okay, it's 1 divided by n squared at most. Okay, and now this is actually just the false positive probability for xj and y. Okay, but what we want is that after you run this entire algorithm, you never get a false positive. Okay. And in order to guarantee that, we need to make sure that for every j from 1 to this upper bound over here, we need to make sure that for all of these j's, you do not get a false positive. Okay? Yeah, so since each of these, so for each particular xj and y, you get a false positive with at most 1 over n squared probability. And since what we're doing is we're considering basically order n possible j's. Okay, so then we want to make sure that for all of these j's, you don't get a false positive. And now this probability is going to be, we're going to look at how many j's we have, okay, times the probability that each one of them is a false positive, right? And so this product is going to be an upper bound on the probability that any of these j's is a false positive. Okay, so this is like this is called the union bound. Right, so the union bound is that if you take two events A and B, right, then the probability that either A or B happens is at most the sum of the probability of A and the probability of B. Okay, so this holds for any random variables, right? We don't need any assumptions about between A and B, but so the probability that so if you have a set of events, the probability that any one of them occurs is at most the sum of the probabilities of each individual event. Okay, so now here our individual events are that one particular xj and y gets a false positive, right? And this has at most a 1 over n squared probability. Okay, and then because we have this number of j's in total, then the probability that any j creates a false positive is at most the sum of all of these individual 1 over n squareds. And so that's going to be, that's at most 1 over n. Okay. Yeah, so that's a union bound. Okay. Any questions about this proof? Right. So what we're saying is that this algorithm has a at most 1 over n probability of false positives. Okay. Any questions about that? Okay. All right, so there are still a few more things we need to do for this algorithm. Okay, so we bounded the false positive probability, but now we need to look at the running time. Okay, because we're trying to get this we're trying to get a an order n plus m running time for this Monte Carlo version of the algorithm. Okay, and now the problem is that this algorithm works by computing fingerprints at all of these different j values, xj values. And if you just do this in a naive way, right, to compute the fingerprint in a straightforward way, then what you need to do is you need to convert x of j to an m-bit number, this number over here, right? And then you need to take in modulo p. And so this would take you order m time just to compute the fingerprint at one j location. Okay, and furthermore, you have to do this for all of these different j's. Right, so they're basically order n different j values. And so if you do this naively, this is actually going to take you order m times n time, okay, not m plus n. Okay, and so therefore we have to somehow not do this naively. Okay, so it turns out that there's a trick to computing these fingerprints. Okay, and the trick is that suppose you've already computed the fingerprint of x of j. Okay, suppose you know that already. Then you can very efficiently compute the next fingerprint, the fingerprint of x of j plus 1. Okay. If you don't know fingerprint of x of j, then to compute the fingerprint of x of j plus 1, you would just have to do this naive calculation over here. But if you already know the fingerprint of x of j, then the next fingerprint can be computed very easily, okay, very quickly. And the reason is because x of j plus 1 and x of j differ in only 2 bits. Okay, so I'll just show you the diagram over here, right? So then here, you see on the bottom over here, this is x of j, right? It starts at the jth bit, right, and then runs for m bits. Okay, and x of j plus 1 starts at the next bit and then also runs for m bits. Okay, so therefore these two strings only differ in 2 bits. Okay, and in fact, if you know the fingerprint of x of j, okay, then we can compute the fingerprint of x of j plus 1 using this formula over here. Okay, so what is this formula saying? Okay, this formula says that if you already know the fingerprint of x of j, then to get the next fingerprint, the first thing you do is, okay, so I'm going to answer the question after I talk about how we do this computation. Okay, all right. So what this formula over here says is that to compute the next fingerprint, right, the first thing you do is you take out the jth bit over here. Okay, this is the most significant bit in x of j. Okay, so to take that out, you just subtract 2 times m minus 1 times this bit. Okay, that's equivalent to taking out this bit out of the, so here you've got like an m bit number, right? If you want to take out the topmost bit, you just do the subtraction over here. Okay, and then after that, you need to take the remaining part over here and you need to shift it to the right by 1 bit. Okay, because now the most significant bit is going to be x of j plus 1. Okay, and to do the shift, you can just multiply by 2, right? So you subtract out the previous most significant bit, you multiply by 2, and then lastly, you add in the least significant bit. Okay, and then after you do all that, you take things modulo p. Okay, so therefore you have this equation over here, which is you can get the next fingerprint from the previous fingerprint just by doing like a few more operations, a constant number of operations. Okay, so yeah, so we have that computing the next fingerprint from the previous fingerprint takes order 1 time. And so that allows us to compute all the fingerprints in order n time. Okay, because, or actually I guess it's order m plus n time. Okay, but m is less than n, so therefore it's order n time. Okay, because what you do is you first begin by computing the first fingerprint. Okay, this is actually going to take you order m time. Okay. But then after that, all of these remaining fingerprints, right? All of these remaining fingerprints, you can just use the previous fingerprint to compute the next one in constant time. Okay, so then you can do this for all of these remaining j's, right? So there are order n of these remaining fingerprints, and you can compute all of them in constant time. And so therefore, therefore computing all of these fingerprints for the xj values altogether takes you order n time. Okay, and then also computing the fingerprint of y takes you order m time. Okay, so therefore, this algorithm basically just involves comparing all of these fingerprints to each other, and this is going to take you order n plus m time. Okay. Any questions about this? Okay, yeah, so there's a question over here. So let me read this question first. If p is too big, then we can't simplify the question enough. If p is small, there's likely to... Oh, right, yeah. So, so the way that we chose p is, where is it? Right, it's based on how we chose t, okay? Right, so we choose t to be this value, okay? So, so our analysis shows that if you choose t to be this value, okay, then you've got a low false positive probability, right? And then furthermore, so if you choose t to be this value, then if you take the log of p, okay, log of p is basically going to be order of log n and log m, okay, plus order of log m. So it's just basically order log n, okay. And now what we're assuming is that, so we need to do this comparison over here, right? And this is a comparison between two numbers which are at most p. Okay, so these numbers have log p digits in them. And because log p is equal to order of log n, okay, then our assumption is that you can actually compare two log n bit numbers in unit time. okay, in constant time. Okay, it's kind of like how you can compare, you know, if you have a computer, you assume that you can do 64-bit arithmetic operations in constant time. Okay, because you're, so here, you know, 64 is basically equal to our log n. It corresponds to our log n. Okay, and we assume that you can do these arithmetic operations in constant time. Okay, so that means that by choosing this p, we get a pretty low error probability. And furthermore, you know, you can compute all these fingerprints and you can compare all of them in a total of m plus m time. Okay, so that p balances these two things that you said. Okay, between the false positive probability and the running time. Okay, yeah. So any other questions? Okay, so all right. So then the final thing we're going to do is we're going to convert the previous algorithm, which was a Monte Carlo algorithm, right? So it can give you false positives. Okay, well, let's say that you, okay, network is unstable, but right, let's say that you want to avoid false positives. Okay, so then what you can do, so then now we're going to convert the previous algorithm, sorry, to a Las Vegas algorithm, which always gives you the right answer. However, the running time is now can change. Okay, it's a random variable now. So the way the Las Vegas algorithm works is that we're going to run the Monte Carlo algorithm. Okay, the previous algorithm. Okay, and if that algorithm never produces a match, okay, then we're going to say that y does not match x. Okay, and this is correct because we know the previous algorithm never produces a false negative. Okay. Right, so if there actually is a match somewhere, the previous algorithm is guaranteed to detect that match. Okay, so if the algorithm the previous algorithm never detected any matches, then that means that y actually does not match x. Okay. On the other hand, if the previous algorithm does detect a match somewhere, okay, let's say it says that x of j and y are a match. Then what we're going to do is we're actually going to just directly check whether x of j and y match. Okay, we're not going to compare their fingerprints anymore because that can be that can have false negatives. Okay, we're just going to directly compare these two bit strings, these m-bit strings. That's going to take us order m time. Okay, now if you know, if when you do this comparison, if they actually do match, okay, then great, we found the match. Okay. On the other hand, if we had a false positive, okay, then you know, if these two things actually do not match, okay, then we're just going to sort of give up. Okay, we're going to start the entire algorithm over, and then we're just going to do the most naive brute force approach to match y and x. Okay, and that's going to take you order m plus n time. Okay, so that brute force approach is basically you know, if you have x is like what is it, 1 1 0 1 0 or something like that. Okay, and if y is something like let's say it's 0 1. Okay, right. So then you're just going to try to match y to all possible positions of x. Okay, so you try over here, right? This is going to take you order m time, right? This is length m, this is length n, right? If it doesn't match, you try the next one, order m time, and so on, right? So in total, you're going to try you know, m minus m possible positions, and that's going to take you at most this amount of time. Okay, so that's our Las Vegas algorithm. We run the previous algorithm, and if it gives us an answer, right, then we're going to check that answer, right? And if it actually was a false positive answer, then we're going to do our brute force thing. Okay, so now you can see that this new Las Vegas algorithm, right, it's possible that it runs in you know, order m plus n time, sorry, order m times n time. Okay, it's possible that it's very slow. However, we're going to show that the expected running time is still going to be order m plus n. Okay. All right. So, all right. Now, first of all, this new algorithm is always going to be giving the correct answer. Okay, because yeah, because you just directly check for false positives. And now, the expected running time of this new algorithm is going to be so what you do is you take the probability that you do not have false positives. Okay, times your running time if you don't have false positives, right? Plus the probability that you do have false positives, times running time if there is a false positive. Okay, so that's going to be the expected running time of this algorithm. Okay, now the probability that you do not have false positives. Okay, so this is so what we showed is that the probability of false positive, right, is going to be at most 1 divided by n. Right, that's what we proved earlier. Okay, so the probability that you do not have a false positive is going to be, this is at least 1 minus 1 over n. Okay, and this running time when you do not have a false positive is going to be order m plus m. Okay, so therefore, if you take the product of these two things, right, then the first term is at most m plus m. Okay, and the second term over here, this term over here, right? Well, this is your false positive probability is at most 1 divided by n. And then if there is a false positive, you might have to do this brute force thing, right? Which is going to take you m times n time. Okay, so therefore the second term is going to be at most order m. Okay, and so that means that the total expected running time is just the sum of these two terms. And so the total expected running time is m plus m. Okay, yeah, so now we have a Monte Carlo algorithm which always gives you the right answer, and it still has this optimal expected running time. Okay, are there any questions about this? Any questions about anything? Okay, all right, so then that's all we have for this, sorry, the previous lecture. So that finishes the previous lecture. Where's my mouse? I can't even see it. All right, so then next we are going to move on to today's lecture, which is on the topic of Chernoff bounds. Okay. Right. So Chernoff bounds are not, so they're not a randomized algorithm. Okay. Instead, Chernoff bounds are a way that you can analyze the complexity of randomized algorithms. Okay. Yeah. So they're a method for analysis. So they're kind of a mathematical tool to analyze randomized algorithms, and they're a very widely used tool. Okay. So that's why we're talking about them, because if you do any sort of randomized algorithms, you're going to see these Chernoff bounds come up all the time. Okay, so the idea for Chernoff bounds is, so what we're trying to do over here is to look at, is to compare a random variable to its expectation. Okay, because the situation that you usually are looking at in computers, in these randomized algorithms, is that suppose you know the expected running time of an algorithm, right? Like the previous string matching algorithm, right? We know the expected running time. However, each time that you run this algorithm, you might not get exactly this expected value, right? The running time can differ. Okay, and now the question is, how likely is the value? How likely is a random variable to differ from its expected value? Okay, yeah, so that's the question. Okay, so for example, suppose you flip a fair coin 100 times. Okay, then you expect to get 50 heads. Okay, however, you can get not 50 heads. Okay, so now you want to look at what's the probability that you get, for example, 60 heads, okay, or 80 heads, or 100 heads. Okay, what's the probability you actually deviate from your expectation? Okay, so if we can analyze problems of this sort, then if you're given some sort of randomized algorithm and you know the expected running time for that algorithm, then sometimes it's possible to use these Chernoff bounds to say that the probability you deviate from this expected running time is very small. Okay, and that's what you want, right? You don't want a very large sort of variance around your expectation, right? You want the value of your random variable to be tightly concentrated around your expectation. Okay, and this Chernoff bound gives you very strong bounds on how tightly, how tight these values are about the expectation in certain situations. Okay, so Chernoff bounds can only be applied in certain situations, but these situations come up quite often in randomized algorithms, and if the situation occurs, you can get a very strong bound with Chernoff bounds. Okay, so before we talk about Chernoff bounds, we're going to talk about a few other probabilistic bounds. Okay, so these bounds are, first of all, they're sometimes useful in themselves. Okay, so sometimes you can just directly use these bounds. Okay, and also these bounds are also used in the proof of the Chernoff bound. Okay, so that's why we want to look at them. However, the problem with these bounds is that they are not as tight as the Chernoff bound. Okay, so for example, the Chernoff bound might say that something has a very, very low probability. Some bad thing has a very low probability of occurring. Okay. On the other hand, these other bounds cannot give you such a tight bound. Okay, they might say that, well, there's not a very, very high probability that this bad thing happens, but they cannot guarantee that there's a very low probability that this bad thing happens. Okay. All right, so these bounds are weaker than the Chernoff bounds. On the other hand, these bounds are more general than the Chernoff bounds. Okay, because I said the Chernoff bounds only apply in certain situations. Okay, whereas these other bounds can apply in a larger range of situations. Okay, so the first bound we're going to look at is this thing called Markov's inequality. Okay, yeah, so sorry, I should have some animation here, but yeah, so somehow they disappeared. All right, so what this Markov inequality says is that suppose you have a positive random variable. Okay, meaning that this random variable can only take positive values, or at least non-negative values. Okay, yeah. So you have this non-negative random variable x, right? Then the probability that this random variable is larger than some value a. Okay, so for any value, any positive value a, the probability x is actually larger than a is at most the expectation of x divided by a. Okay, for any a, for any positive a. So as an example of using this, suppose you want to look at suppose x is the number of heads that you get in 100 coin flips. Okay, so that's definitely a non-negative real random variable. Okay, all right. Now the probability, so you expect to get 50 heads. Okay, and now the probability that you get more than 60 heads using Markov's inequality is going to be at most the expectation, which is 50, right, divided by a. So that's at most 5, 6. Okay, so the Markov inequality says that you have no more than a 5/6 probability of getting more than 60 heads. Okay. All right, now, by the way, this is kind of a weak bound, right? Because actually, if you flip a fair coin 100 times, you have a pretty low probability of getting more than 60 heads. Okay, that probability is a lot less than 5/6. Okay, but because Markov's inequality is weak, it can only give you this, very sort of weak guarantee. Okay, now let's prove Markov's inequality. So yeah, so it's a pretty simple proof. So suppose for contradiction that the probability that you get a value larger than a is actually larger than the expectation divided by a. Okay. Now by the definition of expectation, right? So let's just write out the definition of expectation. So that is that you take all of the possible values of x and then you multiply by the probability of getting each of those values, right? And you sum that. Okay, and because all of these x's are non-negative, okay, now what you can do is you can take this big sum and you can just take out some of the terms. Okay, so let's take out the terms. Let's take out all the terms where x is less. Where x is less than a. Okay, let's remove all of those terms. Okay, all right, and then what you have is that so that's not going to make the sum smaller. Okay, because x is non-negative. So then now you have a just the remaining terms are you sum up over all of the x's which are larger than a, and then you you take each x times the probability. Okay, and now this is going to be at least equal to so all of these x's are at least a. So you can just pull the x out, right? And then you're left with just the sum of these probabilities for all the x's larger than a, but then that is simply the probability that x is at least a. Okay, multiplied by a. Right. And now by assumption, right, by this assumption, you have that this probability here is larger than the expectation divided by a. Okay, so then you plug it in, and then you get that this whole thing is equal to the expectation. Okay. And now you have a contradiction because you're saying the expectation is going to be larger than the expectation. Okay. All right, so that proves Markov's inequality, and yeah, and we saw an example of how to use Markov's inequality. Okay. But again, this inequality is very weak, okay? Because let's look at another example, right? So let's say that you want to look at the probability that if you flip 100 coins, you want to look at what's the probability I get more than 101 heads. Okay, well that's actually 0, right? Because I flip 100 times, I'm not going to get more than 100 heads. Okay. However, if you just use Markov's inequality, you have that this probability is no more than 50, which is your expectation, divided by 101. Okay, so that's like 49%. Okay, so Markov's inequality actually gives you kind of a useless bound in this case. Okay, so then let's look at stronger. Okay, right. So it's a weak inequality. However, the advantage of Markov's inequality is that we don't make any. You almost do not make any assumptions about x, the random variable. Okay, so as long as it's non-negative, then you can use Markov's inequality. Okay, yeah, we don't need x to satisfy any special properties. Okay, and so therefore you can use Markov's inequality in many situations, and in fact you can use it to help prove these stronger bounds, like the Chernoff bounds. Okay, now we're also going to look at another inequality, which is called Chebyshev's inequality. Okay, so this one says that, yeah, suppose you have a random variable x, and then you take any positive a. Okay, now the probability that x deviates, so we're going to look at the absolute value of the difference between x and its expectation. Okay, so the probability that x deviates from its expectation by more than a in either the positive or negative direction, okay, is going to be at most the variance of x divided by a squared. Okay. Yeah, so that's Chebyshev's inequality, and actually you can prove Chebyshev's inequality using Markov's inequality. Okay. So the way to do this is that well, the variance of x is simply the expectation of x minus its expectation squared. Okay. So therefore, if you apply Markov's inequality, right, then the probability that that this thing is larger than a, right, is equal to the probability that this thing squared is larger than a squared. Okay, which is by Markov's inequality, that's going to be at most the expectation of this term, which is the variance, okay, divided by a squared. Okay, the expectation of this thing, right, is equal to the variance. Okay. Yeah, so that proves Chebyshev's inequality. Okay, and Chebyshev's inequality is actually stronger in certain cases than Markov's inequality. Okay, so for example, let's go back to this previous example about looking at the number of heads in 100 coin flips. Okay, so now if you apply Chebyshev's inequality, we have to compute the variance of this number of the number of heads in 100 flips. Okay. So for each flip, right, the variance of each individual flip is 1/4. Okay, you can just compute that directly. And so since all of these flips are independent from each other, the variance of all the flips, of all 100 flips, is just 100 times 1/4. Okay. And so now you can apply Chebyshev's inequality, and you can say that the probability that x differs from its expectation by more than 10, either in the positive or a negative direction. Okay, so either you're getting more than 60 heads or less than 40 heads. Okay, the probability that this happens is at most the variance divided by a squared. Okay, and so this is going to be 1/4 by Chebyshev's. Okay. And now we're just so now if you only care about the probability you get more than 60 heads. Okay, so this probability over here is the probability that you get either more than 60 or less than 40 heads. Okay, but these two probabilities are equal to each other, right? You have the same chance of getting more than 60 heads or less than 40 heads. Okay, because you have exactly a 1/2 probability of getting heads. Okay, so therefore the probability of getting more than 60 heads is going to be 1/2 of this, right? So yeah, so that's going to be 1/8. Okay. And now, if you compare this to Markov's inequality, right? There we only said that the probability of this happening is less than 5/6. Okay, so you can see that Chebyshev's is actually stronger than Markov. Okay. Okay, all right, so that's sort of like a build up to the thing that we really want to do today, which is the turn-off bounds, okay? All right, so now the turn-off bounds are, again, they're bounding the probability that a random variable differs from its expectation. Okay? However, for the turn-off bounds, we're not looking at arbitrary random variables anymore. Okay, we have to look at a special type of random variable, where we can only look at random variables which are sums of independent random variables. Okay, so suppose you have a random variable x, which is a sum of n independent random variables, okay, for some n. Okay, it's important that all of these random variables are independent from each other. Okay, then the turn-off bound tells you how likely x is to deviate from its expectation. Okay, and the intuition is that the larger n is, right? So the more random samples you take, the more you expect x to be similar to its expectation, right? Like if you take n to approach infinity, then you expect x to exactly equal its expectation, right? And so as you make n larger, then x should approach its expectation very quickly, okay? At least in relative terms, okay? So if you just want to look at, is x within like, 10% of its expectation, right? Then as you take more and more samples, it's more and more likely that x is within 10% of its expectation. Okay? And in fact, the rate at which x, the rate at which this probability, so if you look at the probability you differ from your expectation by more than 10%, okay, that probability should decrease. Okay, and in fact, by the turn-off bounds, it's going to decrease exponentially fast. Okay, yeah. So as a concrete example of this, suppose you flip a fair coin n times. Okay, so then you expect to get 50% heads. Okay. So now you can look at what is the probability I get at least 60% heads. Okay, if I flip for n times and I keep making n larger and larger. Okay, so now this probability that you get more than 60% heads, right, that should decrease. Okay, so in fact, if you look at a small n, okay, then it's actually quite likely that you get more than 60% heads. Okay, so if you look at n equals 10, okay, so what's the chance you get at least 6 heads? Well, that's actually a pretty high probability. Okay, 38%. But now if you make n larger, right, then the probability is going to decrease. Okay, so if you keep making n larger, right, then once n gets to like 100, right, now you only have like a 3% chance of getting more than 60% heads, of getting more than 60 heads. Right? Yeah, so in fact, I plotted these probabilities. So here n is on the x-axis, right, and then here this is the probability that you get more than 60% heads. Okay, so if you plot that out, you can see that this probability is decreasing, and it's decreasing exponentially fast. Okay, so basically the turn-off bounds are going to capture this phenomenon. Okay, so right, so now let's actually define the turn-off bounds. So there are actually several variations of the turn-off bounds. Okay, and the reason you have these different variations is because there are a couple of parameters in the turn-off bounds. And so for different parameter settings, there are different variations which are easier to use. Okay. Yeah, so I'll show you all of these different variations. But basically, they all say the same thing. Okay, so intuitively, they're all saying that as you take more and more samples, then x is gonna then a random variable x, which is the sum of a bunch of other random variables. Okay, that's gonna approach its expectation exponentially fast. Okay, so more precisely, so suppose you have a bunch of random variables, x1 up to xn. Okay. And let's assume that they're independent. Okay, this is important. Okay, and furthermore, suppose that each of these random variables is just an indicator variable. Okay, so it can only take on values 0 or 1. Okay, but it can take 0 or 1 with different probabilities. Okay, so for each for the ith random variable, it's got a pi probability of being 1 and a 1 minus pi probability of being 0. And now let's let x be the sum of all of these random variables. Okay, and let's let mu be the expectation of x. Okay, which is simply the sum of all of these individual expectations. Okay, And now we're going to look at what is the probability that this x differs from its expectation by a factor of more than delta. Okay, so for example, if delta is like 0.1, then you're saying, what's the chance that x is larger than its expectation by more than 10%? Okay. Right, now, as I said, there are sort of different versions of the Chernoff bound, and one thing it depends on is what your delta is. Okay, so so if your delta is between 0 to 1, okay, then the probability that your random variable is larger than your expectation by a factor of more than 1 plus delta. Okay, this is going to be at most e to the negative mu times delta squared over 3. Okay. Right, so this delta squared over 3, this is just some sort of constant, right? So if you set delta here to be 0.1, right, then delta squared over 3 is just what is that? It's like 1 over 300. Okay, right. So it's just some sort of constant over here. Okay. And this mu, right? This mu is your expectation. Okay, the expectation of this sum over here. Okay. And now what you can see is that the more of these random variables you have, right, the larger n is, right, then the larger x is going to be, right, and also the larger mu is going to be. Okay, so this means that as you increase your number of random variables, as you increase n, right, then this probability here is going to decrease exponentially fast. Okay. All right, so that's for delta in this 0 to 1 regime. Okay. Now, if delta is larger than 1, then we're still going to look at what's the probability you get more than 1 plus delta times your expectation. So this bound is basically the same, except for this constant factor here is a bit different. Okay, so for the previous case, the constant factor was delta squared over 3, right? And now it's going to be like delta log delta divided by 3. Okay, but you still have this exponential dependence on the expectation. Right, and the final part of this of the first version of the Chernoff bounds is for now. Okay, so this is for delta between 0 to 1, right? But now, what if you want to look at the probability x is less than its expectation? Okay, so here x, you're looking at what's the probability x is larger than its expectation, and in the final case, you're looking at what's the probability it's less than its expectation by a factor of more than 1 minus delta. And again, this is going to be, so you have this constant term involving delta over here. And otherwise, it's going to be exponential in the expectation. Okay, so you see that in all three cases, you have this exponential dependence. Oops. You have this exponential dependence on the expectation. Okay, and then the constant terms are the only things that differ in these three cases. Okay, so that's the Chernoff bound, or at least one version of it. Okay, we're going to see how to apply these bounds later, but this is what the theorem says. Are there any questions about this? Okay, right, so now before we look at applications, so let's first look at sort of intuitively why this would be useful. Okay, because as I said, Chernoff bounds are used in many places when analyzing randomized algorithms. Okay, so the reason that Chernoff bounds are so useful is because many randomized algorithms do things in independent stages. Okay, so for example, if you think about the randomized quicksort algorithm, right? So the way that worked was that you have these stages where in each stage you have an array, and then you pick like a random pivot element, and then you use that to break up your array, right, into two parts. Okay, and then once you break it into two parts, then you recurse on those two parts, and that recursion is independent of what happened in the previous calls to quicksort. Right, so you have all of these independent stages. And often for these independent stages, if you just look at the cost of each stage individually, it's easy to compute the expected cost. Okay, because it's just one stage, right? It's not like many stages together, so it's easier to compute the expected cost. Okay, and then the total cost is just like the sum of all of these individual costs. Okay, so for example, for quicksort, right, each stage you have to break up the you have to break up the array into two parts, right? So you can compute the expected cost easily because all you need to do is you want to find a good pivot, which is ideally your pivot is exactly the middle element. Okay, but you don't need to have exactly the middle element. So even if you have something which is in the middle half of all of the values, then that's still going to give you good performance, right? And so if you just need to look for a pivot in the middle half, then you've got a good probability that this actually happens, right? You've got a 1/2 probability that if you pick a random pivot, it's going to lie within the middle half of the values. Okay, so each stage, so let's say that a stage is good. Let's define a stage to be good if you can pick a pivot in the middle half of the values. Okay, because if you pick one of those pivots, then you break the array into pretty even sides, right? And then overall the execution is fast. Okay. So you have now at least a 1/2 probability of a stage being good. Okay, and now if you run for many stages, right, because you have to keep recursing, so you have to run for many stages, right? Then each of these stages has a 1/2 probability of being good. Right? So you expect that if you run for let's say k stages, then you have at least k divided by 2 good stages. Okay, you expect to have k divided by 2 good stages. Okay. Of course, when you actually run quicksort, you can deviate from this expectation. So your actual number of good stages can be different than k over 2. Okay. But you can also you can use the Chernoff bounds to show that the probability that your number of good stages deviates from k over 2 by a large factor. Okay, this is a very small probability. This is an exponentially small probability. Okay, so that so if you use that kind of approach, you can use that to show that not only is the expected running time of randomized quicksort n log n, right? It's also very, very likely that you get n log n performance. Okay, you have for example, you have a very you have an exponentially small probability of getting something like n times log squared n performance as opposed to log n log n. Okay, yeah, and that's again because you can analyze each of these quicksort stages independently, and then the total running time is just the sum of the running times for each individual stage, right? And because each individual stage is you have a 1/2 probability of getting a good individual stage, then the probability that you get lots of bad individual stages is very low. And so that means that overall your running time is going to be close to your expectation. Okay. So that's kind of like the arguments that you typically use when you analyze things using Chernoff bounds. Okay, so that's like the intuition for why Chernoff bounds are useful. Okay, and and as I said, there are sort of different variations of the Chernoff bounds. Okay, and then so for certain values of this delta factor, right, you're going to get tighter bounds with some variations. But basically, intuitively, they sort of do the same thing. Okay. Right. So now I'm going to give you 2 other versions of the Chernoff bound. So theorem 2 over here is actually sort of a very general form of the Chernoff bound. Okay, but you can also see that it's more complicated, right? So this is why we have these other forms in theorem 1, okay, because they're somehow easier to use than this more general form. Okay, but what this general form says is that again we have a bunch of these random variables, right? X1 up to xn, and then x is and each of these are 0, 1 random variables. Okay, and then x is going to be the sum of all of these x1s up to xn's. Okay. And now for any delta here, right? Delta is how much you deviate from your expectation, right? So the probability that you deviate from your expectation by a factor of more than 1 plus delta is going to be at most this expression over here, which is kind of complicated. Okay? But the thing to look at is that you have this mu, which is the expectation. Okay. Sorry, that should be negative mu. Yeah. So sorry about that. Oh. Wait. Oh no, it is positive. Okay. Yeah. Okay, yeah, so you have this thing over here. Wait, is this, let's see, did I type this incorrectly? Sorry, let me just go look at one thing. So yeah, so this should be like a negative thing over here, right? let's see. So I'm gonna check something. Okay, so one second. Okay. All right. So yeah, I guess no. I mean, this formula is correct. Okay. Anyways, this is a correct formula. Okay. Yeah, and then if you plug in like different values for delta, right? So if you so you can kind of imagine that if you plug in different values for delta, then you're going to get all of these different forms of the Chernoff bound, right? So basically, theorem 1 is a special case of theorem 2 for different values of delta. Okay, right. Okay, so and then we'll talk about one final form of this Chernoff bound, which is that now so suppose your random variables are not 0, 1 random variables, but they have values which are either -1 or +1. Okay, and also suppose that these things are 1 or -1 with the same probability. Okay, so previously, in theorem 2, you allow these xi's to have different probabilities of being 0, or all the xi's are different. Okay, so each one has a pi probability of being 1. Okay, but now assume that all of these things. Sorry, there should be an I here. Sorry. Okay, assume that all of these things have the same probability of being either 1 or -1. Okay, and now let's let x be the sum of all of these random variables. Okay. And so since each one of them is 1 or -1 with the same probability, then the expectation of each random variable is 0. And so the expectation of the sum is also 0. Okay, so now we're going to look at what is the probability that x is not 0. Okay, what's the probability x is larger than some delta? Okay, and this is also equal to the probability that x is less than some delta. Less than negative delta. I'm sorry, I have lots of typos in here. Sorry about that. Okay, well, it's the same as the probability x is less than negative delta, right? Because it's 1 and -1 with the same probability. And this is going to be at most e to the negative delta squared over 2n. Okay, yeah. So you can see that as you make n large, right, then then you have an exponentially decreasing probability of this happening. As you make delta large, right, then you have exponentially decreasing probability that you are different from 0 by more than delta. Okay, let's see how much time. Okay, yeah. So those are the different forms of the Chernoff bounds we'll talk about. Okay, so there are other forms also, but these forms are quite useful in practice. Okay. So what I'm going to do now is I'll prove the Chernoff bound. Okay, so I'm going to prove a simplified version of the Chernoff bound, and of theorem 2. Right. So theorem 2 is like the most general form of the Chernoff bound, but I'm going to give a proof of a special case of theorem 2. And this proof directly comes from Wikipedia. Okay, so I did a screen capture of Wikipedia. Okay, because they have a very nice proof of this bound, so I didn't want to just rewrite everything, so I just directly took this out of Wikipedia. Okay, all right. So let's go through this. So basically, we can prove the Chernoff bound. So the first step is to make use of Markov's inequality. Okay, so what we're doing is, so the question we want to answer is, what's the probability some random variable is larger than a certain value a? Okay. And so now you can actually, so this is the same as if you multiply both sides by some t larger than 0. Okay, so you can pick any t you want. Okay, so it's the same as the probability that tx is larger than ta. Okay, and now you can also exponentiate both sides. Okay, so this is the same as the probability that this happens. Okay, so yeah, so you might ask, like, why would I want to do this, right? Why do I want to multiply by t and then exponentiate? Well, this is how the proof goes. Okay, so that's it. It actually works out if you do these steps. Okay, yeah. All right, so now we can apply Markov's inequality. Okay, which says that this probability is no more than the expectation of this left-hand side divided by the right-hand side. Okay. All right, so now we want to estimate what this value is. Right, now, because x is the sum of n independent random variables, right? Then in order to look at this top expectation over here, okay? So this is like e to tx, where x is equal to the sum of all of these xi's, okay? Yeah, and so therefore, when you exponentiate the sum, this is going to turn into a product, okay? The product over I of e to t times xi for all of these individual i's, okay? Yeah, so and we need to look at the expectation of that. And now, right, and now because these random variables are independent, okay, then the product of these the expectation of this product is actually equal to the product of the expectations because the random variables are independent. Okay, yeah, if they're not independent, then this is not true. Okay, but because they're independent, then you can actually pull this product outside of the expectation. Okay, so you get that this thing is equal to this thing down here, okay, which is the product of the expectation of each of these individual terms. Okay, and then furthermore, we previously chose t to be any positive value. Okay, so you can choose t to be any positive value, and this inequality holds. And so we can actually choose t to minimize this expression over here. Okay, so you can optimize for t. You can choose some t which minimizes the right-hand expression, right? Because in the end, you want this probability to be small. Okay, so we're going to choose a t to minimize the right-hand side over here. Okay, and later on, we're going to see which t actually minimizes the right-hand side. Okay. All right, so now, okay, so now we have this expression over here, and now we're going to analyze each of these individual terms, each of these individual expectations. Okay, and so here we're going to assume for simplicity, right, because we're just doing a simplified proof, but we're going to assume for simplicity that that all of these xi's are the same. Okay, and each of them has the same probability p of being equal to 1. Okay. And so in that case, if you look at each individual xi, right, then this expectation over here is just, well, you have a p probability of being 0, or sorry, a 1 minus p probability of being 0, okay, times e to the t times 0, right, times this thing, right, plus you have a p probability of being 1, right, in which case you're doing e to the t. Okay, yeah, so this is the expectation over here. Yeah, so you can simplify to this. And then you can also do some calculations, and you can simplify things to this form, okay, based on the exponential formula, based on the power series for exponentials. Okay, so then what we know is that each of these individual things is at most equal to this, right? And so since e to the t times x is, this x is just the sum of n of these individual xi's, right? Then, we just put an n in this exponent over here. Okay. All right. Okay. So now, we're almost done. So now we can choose a t to optimize the right-hand side, to minimize the right-hand side. Okay. So suppose you choose t this way. Okay. You choose it to be log of 1 plus delta. Okay. And also you get to pick what a is. Okay. So suppose you pick a to be, so here this is your expected value, right? Because each variable has a p probability of being 1. Right, and you have n of these variables, which is the sum of x. Right, x is the sum of n of these variables. So n times p is your expected value, and then a here is going to be 1 plus delta times your expected value. Okay, all right. So you take t this way and you take a this way, and now you just plug it into this formula, right? And you have that. Yeah. So if you plug in t over here, right? If you plug in over here, you can simplify this to that thing, right? And then also e to the negative ta power, okay? Because we need to look at this e to the negative ta power over here, right? So if you pick a to be this right-hand side over here, then it simplifies to this expression, okay? Right, and then so now you just plug everything in, and you get that the probability that x is more than 1 plus delta times its expected value is going to be the product of these two terms, okay? Which simplifies to this thing over here. Okay, so that's the proof of the Chernoff bound, of one simplified form of the Chernoff bound. Okay, any questions about this? Okay, so I think in that case, I'm going to stop over here. Okay, so we still have some things to do, which is to apply the Chernoff bound in several examples to see how we can use them to prove these tight bounds that I've been talking about. Okay, but I don't think I have time to go through this example, so I'll just leave this for next time. Okay, so we're going to continue with the Chernoff bounds in the next lecture.